Hey everybody, this video lesson is going to cover the introductory notes for Unit 7. Unit 7 is covered on page 160 in the textbook. It's Chapter 5. We're going to start talking about energy and move on to work. This is one of those concepts that actually has a little bit of overlap between chemistry and physics, and so hopefully you'll either have heard this before or this will be the first time you hear it and you'll hear about it again in physics. First law of thermodynamics states that energy is conserved. It cannot be created or destroyed, which means all the energy that ever was and all the energy that ever will be is contained inside the universe. And that's kind of interesting to think about because energy is just being transferred from one form to another, but all that there was at the beginning is the same that there is now, and that energy happens to be expanding into a greater and greater space as the universe expands, but energy is being conserved. To put it in another way, energy going in is equal to the negative energy going out. So the energy is quantitatively the same when it goes in or out of a chemical reaction or changing a physical process. The energy going in, energy going out is the same number, but the sign changes because positive energy is energy in or endothermic energy and negative energy is energy out or exothermic energy. Another way to express this is using the variable Q. Q is an energy unit. Actually, it's not an energy unit, it's an energy variable. Q is measured in joules. And so Q is energy, and the energy in, positive energy, is equal to the energy out, given off. And before we go any further, it's important that we define a couple of different things. Words, really, and those are system and surroundings. Now, the system is what's being observed. Sometimes the system is a sample of gas, or sample of solid, or sample of liquid. Sometimes a system is an entire chemical reaction. But either way, the observed matter, or the observed situation, is the system. And the surroundings, as you'd probably figure out, is everything that's not the system. Everything outside the system is considered the surroundings. Now, oftentimes we talk about surroundings and system in a closed setting or an open setting. A closed system is when the systems and surrounding are staying in a defined space. Maybe an example is a gas state chemical reaction happening in a sealed container, or even a precipitation reaction happening in the aqueous solution that the reaction is mixed together in. And so the system would be the reaction itself and the surroundings are the liquid. And so the system and surroundings and defining the system and surroundings is an important concept or important part of this conversation about thermodynamics. Now, an open system is obviously not closed. So the system and surroundings are not defined. Well, the system is easily defined, but the surroundings is basically open to the environment, or open to the outside atmosphere. So if you let a chemical reaction happen in an open glass beaker, this system is what's happening in the beaker, and the surroundings could be the entire air outside, could be the entire planet of Earth, or even the entire universe. And so open systems are less easy to work with because the system is not, or the surroundings are not well identified. The next thing I want to talk about is chemical potential energy, or in other words, stored energy that can be used chemically. Potential energy can be stored in three different forms, at least three that I'm going to list. The first is in bonds. So an ionic or covalent bond is a little packet of stored energy. When the bond is broken, the energy is released, but when you create the bond, energy is conserved. Intermolecular forces is another way that chemicals can store energy. An intermolecular force, like a dipole-dipole force or even a London dispersion force, and we'll talk about intermolecular forces in the next chapter at much greater length, but these are weak attractions between molecules, but are still sources of stored energy. And finally, the last one is electrostatic, and that is like the positive-negative attraction between the nucleus and the electrons or even the nucleus and the neutrons, the protons and the neutrons in the nucleus. That's the stored nuclear energy, and obviously we can talk about that at a later date and time as well, but we're mostly going to be talking about it in the form of bonds of chemical reactions. So we're going to talk about something called a potential energy profile, which is basically a graph that represents the reactants and products of a chemical reaction. Let's take a look at these two graphs. One of these graphs will show the reactants starting at maybe a spot up here. So these are the reactants. Now, over time, the reactants form products, and the energy down here is for the products. Now, if the products are at a lower energy than the reactant started as, then there's an overall negative change in energy, or in other words, exothermic. Now, on the other side, maybe your reactants start here and the products are at a higher energy than the reactant started. Now, this situation would be a positive change in energy, or also known as endothermic. And so it's always important to pay close attention to what energy, or what stability, really, because energy refers to stability in a manner of speaking, what stability or energy the reactants start as and finish as in products. If the products finish lower energy than the reactants, then there's an exothermic, or a release of energy, which is oftentimes what you observe. But some chemical reactions, in fact, result in a product that is higher energy or less stable than the reactants. This type of reaction may be easy to reverse. We might have remembered from previous science classes that chemical reactions may be reversible. And these reactions may be reversible, but they do exist. But these are two different profiles of potential energy, one showing an exothermic situation and one showing an endothermic situation. In thermodynamics, energy is more than just heat. Energy is the heat and the work that a system can do or can have done on it. So besides the heat energy being absorbed or released by a system, it's also important to identify or to consider the work of or work done by a system. In thermodynamics, energy is actually defined as the heat plus the work. Now we'll talk about the mechanics behind the work done by a system or the work done on the system, but it's important to know this formula because it's going to be part of your learning objectives, and it's on your formula sheet of constants and formulas given to you for the test. But energy is the sum of the heat and the work either released or absorbed and or the work done by or on the system. So this is the formula. E, energy, is equal to Q plus W, Q being joules of energy and work also in joules. Consider this drawing. If I sketch out just a cylinder, an abstract object, and I label this the system, and of course everything outside the system is the surroundings. Now if I take, for example, and put heat into the system, that is an endothermic situation. And if the system releases heat to the surroundings, then that is considered exothermic. These two concepts are things that you probably remember from last year or in your previous chemistry courses. Energy in or energy absorbed to the system is endothermic. If the system is being released from the system, it is exothermic. But we also need to now consider work being done on the system or work being done by the system. So we'll call this positive W and negative W. Still, the positive and negative mean the same thing. Positive means work done on the system, and negative means work done by the system. In order to imagine work being done on a system or by a system, you need to think of the system as having something having variable volume. And we're going to talk about this in an actual example, but if the system is being squeezed by the surroundings, that means the work is being done on the system, so they're being squeezed in on both sides, and you get work done on the system. But if the system is expanding, it's moving the surroundings and compacting the surroundings, and that's when volume increases, then the W is negative, or the work is being done by the system. We'll show you an actual example here in a few slides. Before we go any farther, let's talk about work. Work is defined as force times distance. The unit of work is also the joule, just like the unit of enthalpy is the joule. They're both measured in joules. Because they're both joules, you can add them together to equal the total energy of a system surrounding pairing. So work has a force variable and a distance variable. So the more force, the more work, or at greater distance that the force is applied at constant force, the greater distance, the more work. And so in terms of distance in chemistry, as I mentioned before, distance is determined by how much volume is expanded or contracted. The system either increases its volume or increases its distance or decreases its distance. And so this concept of D is kind of applied to expanding or contracting gases. Here's how the concept of volume and work is applied. Imagine a chemical reaction that produces a gas. The chemical reaction is down here. We're going to put a chunk of zinc into hydrochloric acid, or just some acid. In this case, it is hydrochloric. This is the net ionic. And it's going to make zinc ions and H2 gas. And the gas produced is going to increase the pressure inside. And in order to alleviate or keep the pressure constant, the volume is going to change through this variable volume piston that you see at the top of this apparatus. So here we are. We're looking at the zinc, and we're going to insert it into the HCl when we say go, and it's going to begin reacting, producing H2 bubbles that are going to bubble up and push on this piston. Now we say go, we tip the zinc over, and you can see the bubbles of H2 starting to form. It's creating H2 gas, and it expands the piston. Now the piston started at this level right here, and it ended here. And so you have an overall volume change of positive change in volume. And so we have a positive delta V up here. Now if this whole thing is the system and the surroundings is what's the atmosphere outside, then since the volume expanded, then it did work on the surroundings. And when the system does work on the surroundings, it has a negative value for W. So you can associate a positive change in volume with a negative work, or work done by the system on the surroundings. And it stands to reason that if you do the opposite, that if the volume is somehow compressed and you get a negative change in volume, then you would have been doing work on the system. Basically, if I take my hand up here and I push down on this piston, it will contract the gas, and my hand, being the surroundings, would be doing work on the system. This is what is known as pressure volume work. If the pressure increases and the volume then decreases, according to Boyle's law, then work is going to be done on the system. But if the system is allowed to do work on the surroundings, the volume will increase, the pressure decreases inside the system, and then that's work done by the system, or a negative W. To put it algebraically like they have in the book, if you take the work, it's equal to the negative P times the change in volume. If the volume is negative, as it's written, then the change in work would be a positive number. But if you multiply both sides by -1, then you flip the sign here, and then this becomes -1. So if volume is positive, then that means there's a negative work, or work done by the system on the surroundings. Now what would this look like in chemical reaction form? Well, all you need to do is look for the moles of gas on each side of the reaction to know whether or not something is expanding its volume or decreasing its volume. Remember, we talked about in the gas laws unit that the number of moles and volume are directly proportional. So if the number of moles goes up, the volume goes up. If the number of moles goes down, the volume goes down. Take, for example, the simple synthesis of creating water from hydrogen gas and oxygen gas. On the left side, on the reactant side, I start with 2 moles of gas and of hydrogen gas and 1 mole. So I have a total moles of 3 moles of gas on the left. Now on the right-hand side, I have 2 moles of gas. And so since the volume goes from 3 to 2, I can expect the change in volume to be negative. It's going to shrink. And that must mean that the work is positive, that the system has work done on it by the surroundings. So look for a chemical reaction that has a imbalance in moles on the reactants and product side. And if they have the same amount, then no work can be done. Or if the volume is not variable, then no work can be done, or W equals 0. 0 joules of work done. So we'll finish up here with some basic calculations, keeping in mind the pressure volume work formula is W equals negative P times change in V. So let's take a look at this first example. A gas expands against a pressure of 2 atmospheres from 1 to 4 liters. So how much work does it do? Well, it's got 2 atmospheres of gas times a change of 4 minus 1, from 1 to 4. So 4 minus 1 is a positive 3 liters. And so I've got negative 6. That is the joules, we'll say, the units of work, negative 6 joules of work. Now the other one has a gas expanding of 3 atmospheres. So this time I have 3 atmospheres, and it's expanding from 1 to 3. So 3 minus 1 is -2. Just kidding, it's +2. But -3 times +2 equals -6. So both of these do equivalent amount of work. 2 atmospheres of gas expanding 3 liters or 3 atmospheres of gas expanding 2 liters both give me a -6 joules of work. So that's how you apply the pressure volume work formula. And that just about takes care of this introductory video lesson on thermodynamics. Thanks for listening.